So now we are kind of moving on to a bit in a granular level for each of these goals. So I will primarily discuss about goal 1 and 2. Goal 3 is something that I will not discuss for, and I will explain later why I do not want to discuss about that. So the first goal is prediction model. So obviously you are doing some sort of prediction, right? And how do you know your prediction is good? To be able to do that, say for example, when you are working on continuous variable in say for example 400 or 500, when you are working on continuous variable, do you remember you have learned something about R square? And R square is something that helps you try to identify whether you have good prediction or not, whether the variables that you are including in your regression are explaining enough the outcome, right? One of the different names of this R square is the coefficient of determination. And so that R square can be one example where you are using this R square to determine whether your regression is good or not. Say, for example, if you have a R square of 0.2 and if another model has a R square of 0.8, which one do you think is the best? In that example, one problem is that when you are fitting your model in one particular data set, and then you are trying to use, so you fit your model in that data set. You have three different covariates and you just say y equal to a plus b plus c, three different variables to build your model based on one data set. And then you are using that same model in an external data, which has the same variables. And then you will see often this is the case that the R square that you will get in your original data versus the new data, you will see in the new data, your R square will be decreased, right? And this is something what we call as model optimism or overfitting problem. That when you are using the same data to create your model and to evaluate your model, then that that model is overfitting your data, and you will get a R square that is higher than the true R square. So this R square that you are getting is known as the apparent R square, the R square that you are getting where you are estimating R square from the same data where you have fitted your model. But think about what prediction means. Say, think about 2009. So if you are using 2009 data to fit your model, your goal is probably to try to see what will happen in a future data. Say, for example, in 2010 or 2020. If that model that you built on 2009 data is not really working well in 2010 data, obviously that model that you have built in that data is not doing a very good job in predicting, right? So the prediction error should be measured in a different data set or in a new observation, not in the same observation based on which the model was built. So overfitting is a problem that can be identified by these prediction error measurements. And part of the reason we have this overfitting problem is because sometimes when you are using a lot of noise variables or variables that are not really explaining your outcome well, then you will see that that this is inducing a lot of noise or variability in your data set, and that will cause your R square to be very high in your original data, but not very high when you are using it externally. So there should be always a bias variance trade-off. What that means is that when you are using it in your own data, you will get smaller standard error or a higher R square. And when you are using it in a different data set, it is doing a opposite job. Just to give you a very concrete example, if you go through the lab material, I'm particularly talking about the part B lab. And you will see in those videos as well that when you are checking your prediction, in the same data, you have a R square of 0.243. When you are using it in an external data, you will see immediately your R square will go down. And you are using it on the entire data. So partially some data were used in fitting the model. Then you will see the result will be somewhere in between, right? This 239 is between 23 and 243. And if you are using a completely external data, then you will see even then, even though the data size is almost double, you will see your R square is still less than the original R square in the original data. So this is part of your lab 3B 4.3. You will see this example in that lab. If you are using your data set to train your model and test your model, the R square you are getting, if that is very different than the R square that you are getting from a external data, that is viewed as a problem. And that is what we term as overfitting problem. So in terms of measuring prediction error, depending on what type of outcome you are dealing with, it can be different. So when you are using the continuous measurements, you can use the R square when you are, or you could use the adjusted R square. That has some added benefit. And you can also use the root mean squared error. So if you go to the lab material B, you will see detailed description on formula of these. And of course, these are some of the materials that you have seen in your previous courses. What may be new to you is some of the measurements that you have to use for your binary outcome. So are you familiar with AUC from ROC? Have you seen area under the curve in your previous courses? So area under the curve is also something that is useful as a measure of prediction error when you are using this binary outcome. People use BR score and this additional R square as well to measure the prediction error. All right, so there are two different concepts that people are using in terms of describing predictive model. You will often hear the term discrimination and calibration, and there is a difference between these two. Discrimination is more about how well your prediction model can discriminate between someone who is diseased versus not diseased. So whatever is your outcome, how well your model can discriminate between these two conditions. And AUC is obviously one measure that we can use to get that. Often this is known as the C statistic. And another idea is calibration, the agreement between the observed and the predicted. So obviously when you have data set, you have some observed data, and when you have a model, then based on that model, you can have some predicted outcome. And the agreement between these two is known as calibration. And usually using the Hostmar-Lemichaud test, you can do this calibration test. I'm assuming that you are familiar with both AUC and Hostmar-Lemichaud test from your previous courses. Why overfitting is really a problem? Overfitting is a problem because if you are using a data set to make a prediction model, and then your prediction model does not do its job, that means it cannot predict well the future data, then that is a problem. But if you are using your same model in your own data, you will always see that you are almost always performing very well. All right, so just to give you an example about overfitting. So say, for example, this is your data set, and these are the data points, and I obviously drew them using my mouse, so it looks horrible. So these are the data points that I have. And then when I fit my least square regression, the ordinary least square regression, I try to fit a model like this. Say, for example, these are the observed data, and this is the future data. And then using the least square, if I even extrapolate to get this prediction, it's not going to be too far away, right? Based on this red line that I have drawn, based on only these yellow points. But if you are getting a model that is very flexible, say for example, if you have a third order polynomial or fourth order polynomial, then your model will look like this. It will be very close to the original data that you have generated. But what happens is that what will happen in the future, predicting based on this model can be very hard in that case. It can go anywhere, like there is no restriction where it can go. So in that case, this will be a overfitting problem where you are trying to fit your data so well that you are sacrificing your ability to predict well in the future. In here, what you can see that you are not fitting your data very well in the sense that there are some deviations here, right? But even though when you extrapolate this model, this will be somewhat different. It is not exactly getting to the point, but at least it is close, right? But in here, after this, what will happen, it is very hard to determine. And whether it will get to that point, it is hard to determine. So this is one example of a overfitting problem. There are some ways, even if you have one data set only, there are some ways to assess how good your R square is, right? And I will get to that point a bit later. So some of the causes are obviously if you have a very small set of data, or if you have a model that is highly parameterized with square term, cubic term, and even more than that, that can be some problem. And consequence is that your R square will be not reflective of a true R square when you fit it in the external data, and the effect estimator can be overestimated as well. So there are two different ways we can try to validate our model, right? So one option is to internally validate our data set. So there are some technique called cross-validation or Bootstrap that we can use to internally validate our data. Or everybody feels better about external validation. And generally what external validation means that, say, for example, you built your model based on 2009 data. If that model also works on a different cycle year, say, for example, 2010 or 2015, and the R square reduction is not significant, by significant, say, for example, for the purposes of this example, I say if it is not more than 10%, I will be okay. It could be geographical. If you are fitting your data set in, fitting your model in Canadian data, and then you are trying to extrapolate it in the US enhanced data, whether that model still works well or not. It can be different source of data or different disease area. If you are working with rheumatoid arthritis, maybe try to extrapolate that model in osteoarthritis and try to see whether that model still works or not. Remember that we're talking about predictive model, not causal model. So changing disease area might still work. In the internal data, one point I mentioned is that apparent validation is something which will be which you need to check whether the R square value that you are getting is too high or not, right? And to check that, there are some ways to do that, and these ways could be split sample cross validation and Bootstrap. Let me go through the split sample first. So in this split sample, say for example, you have a data set of 1,000 patients, and you take 70% of those patients in your training data, and you split 30% of your patient in your test data, and you try to build your model based on your training data, and then you try to test your model based on this test data. So the way it is working, the breakdown is like this. This training data is to build your model. Say, for example, you are using a stepwise regression to build your model. You are using that on your training data. But when you are estimating your R square, you should estimate that from your test data. right? So say, for example, in this particular example, I'm getting a 0.14 and 0.12. So in this case, my overall R square is not decreasing 10%. So that might be acceptable to me. And I say that this R square is the true R square, because remember what was the goal from the beginning? Our goal was to predict the future or predict something that is external to the original data. And towards that goal, this R square is the one that you should be reporting. So obviously you can see if by chance, because you are determining these split by chance, right? Who gets to be in the test set and who gets to be in the training set are by chance. You're selecting them by random sampling. It is highly possible, and it is possible that either in your training sample or in your test sample, you might have some extreme observations. And those extreme observations can either bring down your model or can bring down your R square, right? So that is obviously a problem. So the second concept I'm going to explain is the k-fold cross validation. So in this is the iterative process. So we are again working on the same data set 5 different times. So now, say for example, we have 1,000 data set, and we are taking 200 of these observations separate as a test sample, and we are keeping 800 of this observation as a training sample. We are using this training sample to build our model, and we are using this test sample to get our R square. Again, we are in the second part, we are using a second test set, and we are treating the other parts as training set. And we are using these training sets to build our model, and we are using this test set to get our R square. So you can see, even if where here there might be 1 or 2 people who are extreme, but if you are doing it repeatedly, and then you are getting many different R square from all of these different test sets. And then what would be your true R square then that you would report as the true R square for this prediction purposes? The true R square in that case would be the average of all of these. Usually 5 to 10 cross validations are recommended. So when I say k-fold cross validation, in this particular example, I'm using 5 different cross validation. So usually people use 5 to 10 cross validations. And 5-fold cross validation would mean what? You are keeping only the 20% of the data as test set. 10-fold cross validation would mean you are only keeping 10% of the data in your test set. Generally, if you have a large enough data set, 5 to 10 cross validation is good. If you have a small data set, then do a 10-fold cross validation or even more. And if you want to go to the extreme, that if you have 1,000 data set and you want to do a leave one out, that means you will take 999 of them in the training and 1 in the test set. And you can do that 1,000 times, right? So that would be an example of leave one out. And that is an extreme example of a k-fold cross validation. So even if you are feeling intimidated by this concept, I would recommend you to simply go to the lab 2 material where I explicitly explain all of the different things that you need to do to get all of these cross validation done in a step-by-step fashion. All right, so the third concept is Bootstrap, and Bootstrap is slightly different concept than a cross validation. In a Bootstrap, what we are doing is we are essentially doing a random sampling of the same size. Say, for example, in here, I'm using a data of 3. So there are 3 different persons here, and I'm doing a random sampling of the IDs of the subjects, right? So I have 1, 2, 3. I do a random sampling with replacement with the same sample size. So I want a sample size of 3, but I want to do a sampling with replacement. And one example could be this 1, 3, 3, right? So the number 2 sample is never selected, but number 3 is selected more than once. And in here, you can see 2 is selected twice, but 3 is never selected. So this is with replacement. And this is a very useful technique in the scenario where you do not have a good understanding of what is the true distribution that a particular statistic follows. And then this kind of bootstrap technique is very useful to find out a very good estimate of a standard error. And the same technique can also be used to get your prediction errors. Say, for example, in this example, when you do bootstrap, so in this bootstrap, these samples are selected where sample 2 is never selected, right? So you do a model selection based on this data, and then this is your test data, and this is your training data where you are building your model. So who should be in your test data? In your test data should be some people who were never selected in this data. So the number 2 was never selected in this sample. And in this sample, number 3 was never selected. So that number 3 would be your test sample. And in that way, generally you do bootstrap for 200 to 500 times, and you try to build your R square, and you simply average out all of these R square to get your correct bootstrap, which will be optimism free. Now, one point I just want to mention quickly is that this is one way to do bootstrap. There are many different ways to do bootstrap, and in your lab 3 part 2, you will see there is a optimism corrected bootstrap. This is a slightly different algorithm, but operates under the same principle that you should not try to estimate your R square or measure of performance from the same data where you are fitting your model. So even though the algorithm is slightly different and intimidating, I simply included that algorithm in the lab assignment, not the assignment, in the lab, so that you have a sense that this is not the only algorithm we are using. There are many algorithms people use just to get the optimism correction. So it can happen that you may have a lot of outliers, you may have a lot of influential variables, or even in the modeling side, you might have highly collinear variable that can give you a very high amount of variance inflation factor, right? But we do not necessarily know, just because we have those influential vectors or just because we have those influential points, whether that will significantly impact our modeling R square or not. So both cross-validation and bootstrap are ways to check whether your apparent R square and the optimism corrected R square from bootstrap or cross-validation are different or not. Generally, you will see cross-validation is very popular. Bootstrap is very popular for a different reason, because Bootstrap is a very generalized technique that can be applied in not only checking the stability, but also getting standard error estimates. And there are many different use of Bootstrap. But in terms of checking the model optimism, cross-validation is more popular in my opinion. And finding an external data is very hard almost in all of the scenarios. So internal validation is often the best scenario or the best case the authors can present to support their model. All right, so what should go into your model, right? So again, depends on your research question that you are asking, or research goal you are asking. If it is a prediction goal, then probably does not matter too much which particular covariates you are selecting or not. If your goal is the second one, the causal, then having this subject area expert is something that is highly useful. But I would say, even though the textbook says so, but in terms of building the prediction model, it is not too useful. But say there are some exceptions. Say, for example, if you are using these models to build prognostic factors, right? So in that case, having this subject area knowledge would be useful. There are some rules based on how many datasets you have and how many variables you have. So the general rule is you have to have at least 10 or 20 data points per each coefficients that you are introducing. Note that I'm talking about coefficient, not the variable. There is a difference, and if you go to the lab, you will see what is the difference. And based on that rule, if you have a very small sample size, maybe having too many covariates in your analysis sometimes not give you stable results. And cross-validation can help you in the process of model selection, because you can use R square, AIC, BIC, or any other criteria to choose your model, but cross-validation will help you try to determine whether the model that you are building are giving you a realistic prediction error. And there are some shrinkage methods. We will learn about these methods in a later class when we talk about machine learning. All right, so everybody talks about collinearity. So in terms of collinearity, you will see that if you have high correlations, say for example, these scatter plots almost look like a straight line, right? So this is one indication that your correlation is very high. Another indication is that if you fit a ANOVA, you will see it is significant, but when you fit your regression and you get the T statistics and the significance, you will see that T statistics are, many of them are not significant. So this is one indication that you have some multicollinearity problem in your data, right? So here is a question for you. All right, so I probably got the answer. So in here, what you are suggesting that deleting at least one covariate that are associated with high VIF is a common technique that people use. People also do nothing, and sometimes that is okay, as long as you do not have a standard error that is very high. If your confidence interval width is not very high, then sometimes allowing some collinear variable in your data could be okay. And sometimes people do collapse many variable to single variable if that is possible. Say for example, when you are dealing with many diseases and some of the diseases are collinear with each other, you can simply use some sort of comorbidity index, which is just one index, and people often do that. So in terms of the answer to this, all of these are okay answers depending on the scenario. Especially if you go to the lab for this week, I show an example where I use a model with high collinear variable together, and I use another model where I do not have it. I actually use this approach, right? And you will see at the end, when you do the cross validation, there is not much difference. So this would be one scenario where do nothing would be the best approach. The lab for this week will be a shock for you, because there is a VIF of 100 and still that didn't make much of a difference. So when you take a look at your model output, right? So you see all of the standard errors are, say for example, 2 or somewhere close to 2. And there is one standard error, which is 500. Obviously, that's a problem. But if there is another standard error, which is like 5, that is not a problem, right? All right, so I am going to go through some of the reasons why we need to do variable selection. If you have thousands of variables, sometimes that is a problem. If you are including most of these variables that has nothing to do with the entire analysis that you are doing, that can be a problem. But something that you should not do is, say for example, you find a variable insignificant and you automatically delete that variable. That is probably not the best reason to delete a variable. And model parsimony is simpler model and simpler explanation. That could be one reason for you to choose a smaller model. But remember that when you are under the goal of prediction, then simpler model has nothing to do with it. You are not explaining anything. You are just trying to predict. Prediction is your ultimate goal. So these are, I would say, wrong reasons to delete your variables from the model.